Let's talk about double integrals. But before we do that, I want to remind you, in the two-dimensional case, how we first did the integral of f of x from a to b dx. Okay, so what we do for Riemann sums? We divide the interval ab into n subintervals. They didn't have to be equal. And then we select an xi, any point in each subinterval. And then we evaluated f at that point. And then we evaluate the sum of all of these from 1 to n. Where delta x I is the width of each subinterval. So if f is positive, remember this represented area, and this part represented the height, and this part represented the width of each rectangle, and we added those up. And then we took the limit as the delta x is as the smallest of those goes to 0. I guess the largest. If the largest goes to 0, then they all go to 0 of that. And that was the integral. That's what we define the integral to be if the limit exists. So this is the Riemann sum approach. And we're going to do the same thing for double integrals. This time, f is a function of two variables. And we're going to talk about what the double integral over a region R is f of x, y, dA. So we take R to be a region. Let me just make one up. Okay, there's R. And we're going to divide these into rectangles. And we're going to take, we're going to call the inner partition to be all the rectangles that are totally inside R. Then we're going to take a point in each one of those rectangles. Could be the midpoint or the corners. And let's let that one be inside. Okay, so we're going to sum over all these rectangles the height of the function. So we're going to pick a point. That's what those dots are, points in those subintervals. So the ij has to be I and j because you have rectangles all over. So that kind of represents the height. And then you multiply it times the area of each one of those rectangles. So this is a representation of the area of each of those little rectangles. And this can represent the height We didn't draw this in 3 dimensions yet, but we will. Okay, so the point here in this text, we can either use the midpoint of each one of these rectangles. Let me draw a little rectangle that's represented by one of these, say. And we could take the midpoint, or we could take the upper left corner. We could take any point actually, but the book's going to take the upper left. We could take the upper right. We could take the lower left or the lower right. And like I said, actually you could take any point in that rectangle, but just as you did in a two-dimensional case, you took that point to be the midpoint or the left endpoint or the right endpoint. So that's what we're going to do there. Now, basically, that's it. In 3 dimensions, what this looks like. Okay, say I have a curve here and a curve here. And this is A, and this is B on the x-axis. This is Y, and this is Z. What we're going to do is take a slice right here, and this is the curve J, and this is the curve K. And in 3 dimensions, we have this, here's the surface up here, but say this C is the trace in the surface. And if F is positive, we're going to see that this is going to represent the volume of the solid with this base. And so this right here in the blue, this represents the cross section. And if I write the red, in the red, that's say A of x, is going to be the integral from J to K. Whatever those curves are with respect to y. Okay, so that's going to be area of that. And then the volume, I'm just saying if f of xy is positive, is going to represent the integral of the area of this cross section, which is in blue. So it's going to be the integral from A to B, A of x dx, which is integral from A to B, J to K, so first we're going to integrate that, and then we're going to integrate with respect to x. So it's like partial integration. Now the regions that we're going to pick could be anything, but in most cases they're going to look like this. So we have AB here, and we have our curves. So this is our region, and this is G and H. So this integral would be from A to B, then you integrate G of x to H of x, f of x, y, dy, dx. This represents dA, the area of that region, and this represents the height of that function. And you, another case, it could be from C to D is how you go, and our functions go like this, J, K. So we would integrate C to D, J to K, f x y dx. we would do this first and then integrate with respect to y. And again, that would be the height and times the area would give us the volume if the function is positive. So we'll see that later. But right now, what we're going to do is we're going to do the Riemann sum in this section. And that looks like this. I equals 1 to m. We're going to cut up x, and then we're going to cut up y. It means you're going to take the height in each one of the rectangles, and you're going to add up let's see. And delta A, that's the area of each rectangle. And we're going to take equal same size rectangles, so that delta A is going to be the same thing. And we're going to say that's going to be approximately this double area over the region of the function dA. And again, this point that we're going to take could be the midpoint, or it could be one of the corners of the rectangle. Actually, it could be any point in the rectangle. But look at the example homework problems, and you'll get a good example of what we're doing here.